Imagine a massive engine where the individual gears spin at high speeds, but the main drive shaft is completely seized. This is exactly how most modern enterprises are adopting artificial intelligence. They are pouring capital into AI, but integrating it exclusively into isolated operational pockets. You see intelligence localized in very specific areas. DevOps teams, the groups that unify software development and IT operations, deploy automated monitoring tools. Product developers rely on AI copilots to generate code. QA departments, responsible for preventing software defects, build predictive models to test that code. But look at the connections between these clusters. While the individual nodes pulse with intelligent activity, the dependencies linking them remain manual or broken. The consequence is a bottleneck. Release cycles are blocked by cross-team dependencies. The intelligence loops are not synchronized. Treating AI as an addition to legacy systems limits its impact. Systemic leverage requires a foundational redesign to make the architecture natively intelligent. Enter the INA framework, an AI-native architecture. It serves as a unified operating standard specifically designed to synchronize these fragmented enterprise intelligence loops. Adopting AI features without architectural synchronization creates intelligent chaos. Systemic acceleration requires a synchronized, natively intelligent operational framework. The framework rests on the clean data capability principle. A system's technological capability is directly proportional to its structural data hygiene. Garbage data creates the illusion of intelligence. True operational leverage requires clean, structured, and context-rich metadata. The INA framework begins with Layer 1, replacing fragmented alerts with a unified observability graph. All modules must emit structured telemetry, attach business impact metadata, and broadcast intermodule dependencies. This standardized reporting establishes a shared system state baseline, eliminating siloed monitoring dashboards. Without a unified, structured observability layer, any subsequent automation is blind and incapable of systemic learning. Raw data hygiene is insufficient on its own. In autonomous systems, unmanaged signals create noise, and unclassified signals create critical risk. INA introduces the D-term classification model, the Data Event Taxonomy and Response Model. It acts as mandatory routing logic for all telemetry. The first pipeline is the decision marker, or D, driving automated or human action, like deployment risk scores. Next is the enforcement marker, E, enforcing compliance boundaries and halting systemic risk. An example is an SLA breach, a surface-level agreement defining the minimum acceptable performance standards between provider and client. The T is the trend marker, used for longitudinal pattern recognition. It calibrates long-term structural resilience based on data like MTTR degradation curves, the mean time to recovery, or average time required to repair a failure. Finally, the review marker, R. Ambiguous or edge case signals are explicitly routed here to preserve accountable, non-discretionary human oversight. The framework enforces a strict rule. Any manual gate must explicitly document why it requires review and identify exactly what data is missing to automate it in the future. The DTERM taxonomy transforms passive governance into an active architectural layer. It ensures every single data event has structural intent and accountable routing logic. Let's follow an anomaly flagged as an enforcement marker as it exits the DTERM taxonomy and moves deeper into the architecture. The marker enters INA Layer 2, the autonomous complaint engine. Here, unstructured alerts are obsolete. Every system module must autonomously detect deviations, quantify their severity, and generate a standardized machine-readable escalation schema. This standardized complaint package slides directly into INA Layer 3, self-healing contracts. Under this contract, each microservice proactively declares its known failure modes, establish rollback triggers, and outline predefined recovery playbooks. By standardizing both the complaint and the contract, the system can execute automated healing pathways. It can trigger a localized restart, adjust the system scaling, or deploy a software patch without any manual triage. Anomaly detection without automated healing is merely institutional noise. INA Layers 2 and 3 establish true closed-loop operational resilience. Expanding our view, we reach Layer 4, the cross-module synchronization protocol. This layer connects previously siloed departments. For example, if operations detects a deployment risk spike, Layer 4 automatically signals QA to deepen its testing automation. Or, if the system detects AI model drift in a production environment, that intelligence autonomously propagates updates to all dependent downstream modules. Finally, we reach the capping tier, Layer 5, the business communication layer. This enforces the interpretation stability principle. The core semantic meaning of a system event must not vary, whether viewed by technical, operational, or executive teams. Layer 5 automatically translates intelligence events into context-rich revenue and business impact statements. This removes the manual translation lag that typically slows communication between departments. Cross-module synchronization compounds enterprise productivity. It ensures that every time a localized module learns or adapts, it strengthens the entire operational system. The AINA maturity model outlines a progression for organizations. It maps the journey from Level 1, which relies on fragmented observability, to Level 5, a fully synchronized, self-healing, AI-native enterprise. Progression through these levels is governed by the value equivalent action principle. This ensures that monitoring overhead, governance, and automation efforts never exceed the operational delivery speed or the insight value they generate. As AI systems gain operational autonomy, the governing institution must assume equivalent architectural responsibility. In an AI-native architecture, institutional character is defined by the discipline of its governance. Technological capability operating without the structured accountability of the DETRM taxonomy creates an asymmetry that eventually destabilizes the organization. When decision, execution, trust, and resilience are firmly structured together, the resulting system operates just like a living organism. AINA and the DTRM standard move beyond localized smart features, establishing an enterprise system that is structurally conscious, accountable, and durably resilient.